is here, and I do want you to practice on that. So why I'm setting up the deadline, because the due date is not close. You still can practice on the quizzes. It's not close. It means I'm just coming back randomly to check how many of you have been practiced and who is really care about their grade. If you don't care, I don't even care about you. So that's the thing. That's the trade-off. All right. Then if you're coming back to say, I have just missing 1 point to get a pass grade. And so I would just simply look at history and say, you don't even care about practicing. And why should I care about your grade? Okay. So this is just a feedback from me. So I would, rather than having this kind of, do practice, have a better grade in the final. All right. Any question for me? Any complaints? Any questions? No? Okay. So I have to notify you about something related to the homework 3 that I have discovered a lot of students who is not submitting the Lex.C. Okay. So if you didn't submit Lex.C, it means conceptually your submission is incomplete. It could be leading a 0. But to provide that I am the one who care about you, I will deduct 20 points off. And I will use my Lex.C to test your code. All right? Anything? Yes.
Like I told you, like yesterday, there was already a Lex.C in there, but it was not the one that should have been used.
Should have been used.
Yeah.
Yeah, so that's the thing. We have to figure out what exactly the protocol you are storing your Lex.C file and what exactly token list that you are storing. Then it's going to cost us a lot of time. Then I think the deduction is 20 points is not enough. I didn't get like 30 points, but 20 points for the deduction. Okay. Any other things I may need to know?
Did you vote Lex.C? I want to see how you did it.
No, no. So if I give you the feedback, have you got 100 for that? 95? So we can come up to the office hours, talk about it to how to fix your Lex.C rather than I give you the direct answer. So I want you to improve based on your implementation, not based on my implementation. My logic is kind of different from yours, okay? But I'm not saying, my logic, my implementation is 100% be the one you should follow. But I have good approach to implementing, but you have yours. All right. Any other things I may have? That's it? Okay. So let's get back to the lecturing. Okay. So this lecturing we will cover about how the simple computers is structured and how it runs the program in isolations. We will dive in deep into interrupt mechanisms, essentially how the hardware and software cooperate when an unexpected event occurs. So when we will look at the interface between the hardware and operating system and break down the different types of interrupts that we might encounter. And by the end, you will see how interrupt handling is so important for operating system and how it ties into the real world software behavior. That is our goal. Just remember that. And first, we have to recall the basic structure of tiny machine using von Neumann model. And what do we have here? What is this diagram indicating? What is exactly the ISA we're talking about here? Come on. What's that? Accumulator RSA. How you say it's accumulator RSA? Simply because we have an accumulator register right here. It's called A. And what is this one is indeed some question you may see in the final. I simply just give a diagram, just asking what is exactly the accumulator here? What is the ISA? What is the ISA for this diagram? You are going to say, oh, it's an accumulator, it's a loader store, it's stack base, etc. Okay. So imagine this how a simple CPU can have a few different registers. Just simply, we're just refreshing our knowledge towards this von Neumann machine with the accumulator ISA. Then we have PC. PC is what? Program counter. Program counter for what? Current and next instruction. And PC track to the next instruction's address in a memory address register is hold addresses for memory access and a memory data register MDR to hold the data moving to and from the memory. And the instruction register IR is for the current instruction. That's absolutely current, explicitly saying what is the current instruction. And the accumulator register, which is A. And those are several others we have in the memory part and a memory and arithmetic logic unit, which is called ALU right here. And the design, this design is the classic design for a von Neumann architecture, which is one shared memory holds both instruction and data. Then coming back to a question I may ask you in the final, what is the definition for von Neumann machine? What is the structure for von Neumann machine? It will be more explicitly saying that. Come on. A shared memory holds both instruction and data. That's it. And lastly, we have how it's going to be executed in this von Neumann machine. What is the data flow for this von Neumann machine is that we have the PC feeds address to MAR and the memory sends a instruction back to basically retrieve the instruction from the memory and send it back to MDR, and MDR is holding those instructions and send it further back to IR, and the ALU, the accumulator, will be having some decoding and going to accumulator and register, etc. will go into the ALU for the arithmetics control unit. And since this is just a simple tiny machine, we will use understanding the program and the interrupts. So that's why we set up this review first. Okay, in most digital computers, that CPU follows what is that? It could be fetch, decode, execute. So simply, we simplify it as fetch and execute loop. The instruction at address is fetched to MDR and then loaded into IR. And the PC is incremented to is pointed to the next instruction. And in the decoder, on decoding stage, the control unit examines the opcode to determine what operation is requested and operand are needed. And finally, in the execution stage, the CPU performs operations such as ALU may add or subtract values, or CPU may read or write some values from the CPU or to the CPU, from the memory or to the memory. And in the simple CPUs, this is just simple loops, execute instructions sequentially, one after another. So there's in a more advanced processors, it can be pipelined, but basic idea is unchanged. What exactly the pipeline we're talking about is basically the cycles, clock cycles, how we can parallel processing everything, how we can place each instruction in a parallel phrase. Could be 2 instruction in parallel or 3 instruction in parallel. So just remember this interrupts will break the cycles, and then the interrupt occurs, the CPU will jumps to an interrupt service routine and handles the events, and then resume at the point where it was interrupted. So basically, we have referred all the components in the past. This is a slide summarize all the definition you need to know. It will be coming questions in the final. And do I need to repeat this slide? We have PC, MAR, MEM, MDR, IR, ALU, decoder, and accumulator. Do I need to repeat this slide? It's very straightforward, and we have talked about extensively in our lecture 1. If not, we can skip. Any complaint? Okay, I think it's very straightforward. You can, if you just simply forgot about it, go this slide, review it, all right? If you just simply don't know, come to my office hour and ask, all right? So now we come into the fetch and execute cycles, which is our tiny machine consistent a loop for 4 steps. Remember, 4 steps. We have fetch the execution from the memory using the PC and place it into the IR. PC increments, which is updating the PC to the next instructions address. 3, decoding the instructions. And lastly, executing, which are often involving reading and writing memory and performing automatics in ALU. So that's the exact 4 steps you need to follow. Then simply saying that, what exactly the steps you're talking, only 4 words. 1, fetch. 2, increment. 3, decode. Lastly, execute. Only 4 words. Okay. Now, let's coming back to our lecture 1, and simply we are just refreshing our memory about what exactly the data movement happening between slide to slide, and which is a lot of most students answer wrong. In the midterm exams, we have the data movement. What is actually happening in this data movement? What is MAR to PC to MAR? What is actually happening? So let's just refreshing our memory, all right? So the first data movement we have here is transferring the address of the next instruction from the PC to MAR, which includes in this notation right here. So in other words, the CPU takes the address and it has bookmarked in the PC and placed in onto the MAR, which is connected to the memory. And we denote this operation as this one, and just conceptually thinking this one as it telling the memory that I want to access this location at this address, simply as that. So this is step 1 for the basic fetch cycles, getting the address ready for the memory so that memory knows where I can grab the information and where the data I can deliver, okay, deliver from. So this is a simple copy and address inside the CPU, and it's just a critical first step to fetch any instruction or data from the memory. Then the second data movement we have here is retrieving information from memory into the CPU's data register. So once the MAR holding the address, then from the PC or any address we have requested, the memory will either fetch or store the data. So at least for here, it is fetching the data from the memory. What exactly the fetching is? So memory is a piece of hardware we are dealing with, and MAR is address. We simply you can consider as a one array or 2D array. So we're simply going that index to grab whatever the content inside of it and deliver to MDR. Okay. So for the next one is much simpler. It's simply storing the information from MDR to memory. So storing that information. So MDR is the content, MAR is the address, which is considered can be an index, and memory is the array we're dealing with. So simply return that information back to the array. Any question? Good. And continue with our fetching process. And this is the third step to take the instruction we just fetched and load it into IR. And simply we do this notation and MDR copy into IR. And at this moment, the CPU has instruction in hand, which is inside IR. It can proceed with interpreted and what instruction it is. And essentially the fetch part is complete once the IR is loaded. So at this stage, I may have a question in the final. Just simply ask, what is exactly the content in MDR right now on this slide? What? Instruction. So you should understand MDR is holding all kinds of information. It could be integers, could be flow numbers, could be instructions, could be some other things happening. The MDR is a universal register that is holding all kinds of informations. But specifically in this step, it is holding instructions so that we can moving that instruction or copy that instruction to IR. Otherwise, if it's holding like flow number, integer number, how is it possible that we can throw it into IR? And IR just simply doesn't understand it. That's a specific term, okay? So now let's pause right here to consider what exactly IR we're talking about. And IR will only consist of two parts. One is opcode, one is address, as we can see here. And simply, we're going to further refer this as IR.OP will be accessing the operand opcode and what exactly opcode we are dealing with. And IR.address will be accessing the address part of this IR. Okay, just simply as a metaphor here. And now we move into the final part of the fetch cycles, which is decoding the instruction. The CPU simply sends that opcode from the IR to the control unit of the decoder, which is here, right here. And we denote this step as IR.OP, which is access whatever the operation code we are having stored in the IR, send it to decoder. And essentially, IR operation field will simply hand it off to the decoder, which is the part of the control unit, and which will further interpret which instruction it is. Is it a load? Is it lit? Is it add? Is it jump? Or etc. And it triggers appropriate execution circuitry. And this step does not move the data like the others. Instead, it's just initiate the control signals for the executing phase. So after this step, the CPU will has fetched the instructions and ready to execute it. At this point, our tiny machine knows what exactly the instruction is dealing with, and it can operate the actual operations. Get it? Any question? Yes? No? Okay. So now let's coming back to how we formalize the fetch cycles with simple pseudocode of our hardware. And this slide is simply from our lecture 1. Do you have any questions? So furthermore, we have a couple of our slides just explaining what is actually a pseudocode for the fetch, for the add, for the store, etc. Do you have any question? If not, we can simply just summarize everything and skip over, simply because we have a lot of content to cover. Yes or no? Yes or no? Yes, yes, yes. Okay, so simply as here, we'll just summarize this slide, which is the PC is copied to the MAR is holding address, and then PC increment and doing the fetch the content of the instructions, which is from the memory, placed in the MDR, and the MDR copy that instruction to IR, and lastly, the IR's operating will be sending to the decoder to notice what exactly operation we're dealing with. Simply here is having a notation rather than here saying step 2 and step 3 can be parallel processing. Simply they don't interfere with each other. And you can see the vertical the two vertical bars is indicating it is parallel processing. Okay. Now we come into the loading. Loading is simply as we have the address, IR.address copy to MAR, grab whatever the information from the memory, place in MDR, and this information will further send back to register, which is accumulator register, and then we are going to decode it. And lastly, we have the adding, or not last. Adding is simply we have copied the IR's address to MAR again, and MDR have access place that content from the memory, loading that information to the memory. And what we have here, MDR, is the information and dealing with accumulator, and the result will be stored in the accumulator. And lastly, we have the decoder part, which is set to execute fetch cycle again. That's 0, 0. And last, so this is the step we are storing, which means we have IR the address, placed MAR. Of course, every time we're dealing with access of memory, we have to have a fresh content in MAR. So MAR's unit, and then we have a accumulator stored back to the MDR, and then have MDR stored back to the memory. So lastly, we have decoder sets to 0, 0 means we are going to do the fetch cycle again. Now, the question is, why cannot we simply write whatever the accumulator result back to memory directly? Why we want to go through an extra step, send this information back to MDR and send it back to the memory again? Why we want this extra step? Yes.
Yeah. Storing that and memory. Is that the question?
Mm-hmm.
Oh, well, that's from the back, right? There's no from the
That's correct. That's correct. Simply go back to our architecture. Do we have a line from accumulator directly to the register, to the memory? No, simply as that. So that's the only answer we can have. But once you coming back to more concrete idea, why this design makes sense? It comes for a reason, right? But what exactly the reason behind it? Have you ever think about this? Yes. Not necessarily. So why we have this design? Because of efficiency, simply because of efficiency. Accumulator only dealing with data, integers, flow numbers, is only dealing with some this arithmetic store informations. But MDRs will have a more universal, it have more capacity to hold all kinds of information, universal information, instructions, integers, flow numbers, etc., and have more types of information it can hold. It means it's larger, it means slower. But accumulator is smaller, it means it's fast. So that's the case, efficiency. And so that whenever we go to the MDR and send it back to memory. So that's the step we can only do in once. But accumulator will have multiple many times automatic dealing with accumulator. Okay, so efficiency is the only answer we have. And lastly, we have the tiny machine needs a way to stop execution, which is the halt instruction, often the last instruction of the program that tells the CPU to stop the fetch cycle. And let's say the halt opcode is 07 and the execution of halt is quite very straightforward. So the CPU will enter the halt state and simply stop the fetching of new instructions. In the pseudocode, as you can see here, it simply tells stop. As the program stopped normally. So in practice, this might implement by control unit not setting the decoder back to 0. It could be back to 01 or back to something else that is telling the decoder no more fetching at all. Okay. Now we're coming back to the instruction set architecture of our tiny machine summarized here. This is a more cohesive or self-explained slide that we have everything on the slide. We have fetch cycle, we have loading, we have add and back to store and halt. So the halting will end the program normally. So this ISA gives us a complete but minimal instruction set to run a simple program. But a quick note about our formatting of instructions. So we have talked about a lot of times in the lecture that this machine, whatever the machine we're dealing with, whether it's a stack-based machine or accumulator machines, we're always dealing with one address architecture. So that means every instruction explicitly references one memory address at the most. So simply we have load X, load Y, they are all coming back to the memory address. And in this architecture specifically, the accumulator is implicitly as mentioned in the operand or destinations. So general format will be operation and address. So the key takeaway from this slide is instruction is specify what operation to do and where the memory to do it. That's address is specifying, and the accumulator is involved in most operations by default, not mentioning in this architecture. And so far, what do we have discovered? What we have discussed about is the program running in as an isolated system, just the program and CPU, but simply executing the instructions in sequence, no outside interference. So nobody assuming nothing ever goes wrong. But you should think of how you can write a program, you can running a program just with a CPU. Is that possible for nowadays? What do we have here for this class is what? System software. we have an extra layer to deal with. That is operating system. You have to write a program. The operating system runs it. And the operating system is dealing with the underlayer hardwares. And so what is actually happening if we have something goes wrong and involving with operating systems? Something does go wrong during executions. For example, what if an automatic overflow occurs while performing an addition? So in our current design, so the CPU will just carry what is on the BIS4 on where, potentially producing an incorrect result in accumulator without any indication. But the thing is, we have talked about this. But do you understand what is that overflow means? What is overflow? I know you know that, overflow. We have dealing with in the CIS class, which is a very fundamental class. What is overflow?
It's that type.
Mm-hmm.
So like
Okay, that's good explanation. Is everybody understand that? You sure? Okay, then I'm giving you a example right here to further demonstrating whatever is being said. So example is more understandable. For example, if we're dealing with 2-bit arithmetics, 2-bit in binary, the first bit is 1, 1, and next bit is 0, 1. We are doing addition. Okay, what is the result? What is the result? Come on. 1, 0, 0. Okay, but what is the context we're working with? 2 bits. The result is 3 bits. It means we have overflow happening. Then this digit simply means overflow digits. Okay, in our normal operations, or whenever overflow happening in your hardware wise, whatever overflows, it will discard it. Whatever the overflow discard it. It means your hardware only knows 1101. The summation of these 2 numbers will have the result of 0, 0. Is that correct? Definitely not. So we have to consider, okay, there's an overflow happening. How can we deal with that? So that's the question. Okay. Now, so clearly in our current design, it simply does not deal with any overflow errors. And we want to have a mechanism to detect what exactly overflow happens and how we can do that. Clearly, we need a mechanism to detect such events and take appropriate actions rather than silently continue. And this same concern applies to the other error conditions like dividing by 0. A program bug tries to jump to an invalid address, etc. And in a robust system, especially in an operating system context, we don't want state error or crash everything and then go unnoticed. So we want a system to catch it, handle it, perhaps aborting the systems or triggering error routines. So this is where the concept interrupt comes into play. Just simply think, what do you have here on your computer right now? You have programs, right? And whenever you are writing programs, you could have some mistakes and simply your system is dealing with those programs, whether it's running something. And sometimes your program is frozen and simply closed by itself. That's operating system is doing that. It detects some errors and let you know something went wrong. I have to abort it. Otherwise, my system will be aborted. So your operating system will get frozen. And another idea or another concept or example I can give you is think about your Windows, our Asian Windows. Have you ever experienced a Windows 7, Windows XP, Windows 98, which is you never experienced that. But in Windows 7, I think you might have ever met a condition that a scenario blue screen. blue screen. So that is the system is not protecting the program itself. Simply as you have, for example, an 8 gigabits large memory, and the program is requesting, I want you to use 12 gigabits of memories, and simply is beyond what's your physical limitation in your current design. Therefore, the system doesn't prevent that and directly load that information and go above, basically beyond the limitation, and blue screen appears. So that's the thing. And what we are going to do here is to talk about how we can design the system to exit gracefully. Simply exit the program, not aborting my operating system. Now let's tackle what is the specific errors we are talking about right here, which is arithmetic overflow. We will enhance our hardware to detect this. We will add a flip-flop flag to the ALU that will set an overflow occurs during an operation, such as addition of two positive numbers exceeding the maximum values. In our 2-bit examples, what is the maximum numbers we're dealing with? Should be 1, 1, right? That's the maximum value we're dealing with. So here we are having a dedicated hardware bit placed in our architecture that is we call an overflow flag, which is we call abbreviation in OV. Now, simply detecting overflow is not enough. We also need a plan to what to do when it happens. When it means we are going to extending our CPU cycles beyond just fetch and execute, and we are going to involve this fetch execute cycles into fetch execute interrupt cycle. Okay, get it? From 2 steps to 3 steps. So now, in other words, after executing the instruction, and the CPU will have additional steps where it checks did any special conditions such as overflow happen, and do I need to handle that? If yes, it will handle this in a interrupt cycles. And if an overflow happens, we want to signal an abnormal end, which is a B end or a bend. So to signal the system that there's something went wrong, and basically a controlled crash or stop rather than continue with the bad state. So the idea of a bend means the program has encountered a fatal error, such as overflow, and the system will determine it gracefully instead of letting it proceed incorrectly. All right? So now you can see this architecture. We have modified this architecture, this tiny machine computer architecture, slightly to include the new overflow flag, picturing beside this ALU that we have a flip-flop output that indicating the overflow. Whenever an arithmetic operation such as add, execute, an ALU will set the OV flag to 1 if the result overflowed the numeric range such as 1, 1 plus 0, 1, and we have overflow bit with 1, and simply throw that over bit flow to the OV, set it to be 1, and 0 otherwise. So everything else in the Von machine remains the same. We have PC, MER, MDR, etc. Everything is the same, but the single bit is crucial for error detection, which is OV. In our diagram, as you can see here, OV. And with OV in place, our machine can now catch overflow as soon as it happens. So the next question is, how does the CPU respond to this OV is being set? So for that, we need to discuss some interrupt in more detail. Basically, how the CPU control the logic will react once they see OV equal 1 at the end of the instruction. Now coming to this slide, and what we have now, we introduce this idea of interrupt cycle as part of the CPU's operation. Just simply think this one as an extra step after a normal execute phase of each instruction during interrupt cycle, and the CPU will simply check this special flag such as overflow flag, and will add more flags, more CPU content towards this architecture. We'll soon in our Friday's lecture to see if any required attention. If none of those flags are set, the interrupt cycle will do nothing, and the CPU will seamlessly continue with next fetch as usual. If a flag is set, meaning an exceptional event occurred, and the CPU will perform a series of actions to handle and before moving on. Essentially, our fetch execute loop becomes fetch execute interrupt loop. So every time through after executing the instruction, the CPU will simply ask a question: should I interrupt? And this mechanism is how hardware can automatically respond to the event like errors and external signals. So this is the bridge that we can transfer the control from the running program to some special handling routines in an instant without the program itself explicitly invoking it. Okay, then coming back to your homework 3. Your homework 3 is simply saying, whenever I encounter an error, we'll go to the function and exit 1. That is abnormal exiting. So that is you explicitly say, I need to exit at this time. But now we have a hardware bit to let the system know I need to exit explicitly. Okay, exit or abort this program. So let's consider this a very simple scenario. What we have here is for the interrupt cycles and with our overflow flag. And suppose the CPU has just executed an add and the ALU set OV flag to be 1, meaning overflow happened. So when we enter the interrupt check and we simply called this step as state 05 in our control logic, and CPU will see, okay, OV is 1 right now, I need to take some action. In most straightforward design, the action might be something like this. We perform an abnormal end routine for overflow. Essentially, it stopped the program because it hit an unrecovered error. In practice, it could be meaning printing some error message or halting the system or halting the execution. Halting the CPU know for the instruction from the program will be fetched. That is halting means. But in terms of control signals, then CPU might simply execute halt internally when OV equal to 1. Additionally, we set the control state, set the decoder to fetch 0, 0 in case we were start a new program or cleaning up. So in this naive initial design, the interrupt cycle job is to simply, if overflow happened, then we are going to halt the program. This is a basic form of interrupt handling. It's not very graceful. We'll talk about why in later slides. And it is not graceful. Simply, we are terminating the program and telling we can halt normally. But it ensures we don't continue with bad state. However, halting an overflow is drastic, and perhaps we can do a better job by actually jumping to a special error handling routine instead of outright stopping normally. So this is a more elaborate interrupting handling routine will come on Friday. So let's stop right here. Do you have any question for now? So it's just simply introducing the idea of interrupt. And for whoever is attending on Zoom, thank you for coming. And for whoever is here,